I'm Ryan Grove. This is my wife, Tiffany Grove. We've been having a conversation about the flat Earth. Um, this will be our fourth installment, and I would just like to reiterate that it's not a debate; it's a conversation. And so, once again, I don't have any notes. I haven't prepared to debate. It's you should think of it more as a conversation that you might hear in a bar between two people or something. More than, I'm not trying to convince anybody of anything. I don't think she's trying to convince anybody of anything. It's just sort of
Although conversations in bars aren't really very good.
well, okay, fair enough. But anyway, so last time I did most of the talking, even to possibly obnoxious degrees. So this time I'm going to let my wife Tiffany have more of an opportunity to get her ideas across. So without further ado, my dear.
Well, I wrote out some of my ideas of how I see the universe and our place in it. So,
well, a lot of conversations usually don't have them written out beforehand, but let's just say that this was a conversation you had about it in your head, and now you're sharing it with us. I'm sorry. All right, go.
if we think of the universe as a continuum, continuously expanding as an inverse sphere, and it is an inverse sphere because we are within the universe looking out, being able to look back in time in every direction at the beauty of the stars. We have a process of continuous energy exchange that is formed by the spontaneous absorption and emission of light. This is represented in quantum mechanics by the quantum wave particle function expanding out as an inverse sphere. And in this model, this forms part of one universal process with the inverse square law of Newton's gravity. The wave-particle duality of light is acting like the bits of zeros and ones on a computer, forming a blank canvas that we can interact with, turning the possible into the actual within our own reference frame. Time is an emergent property formed by a process of spherical symmetry forming and breaking that we see and feel as the future continuously coming into existence, light photon by light photon, relative to the position and to the energy momentum of the atoms. The extra dimensions of string theory and the parallel universe of Hugh Everett and his many world interpretation are just future possibilities and opportunities in our one three-dimensional universe of continuous energy exchange, or we could call it continuous creation in the mathematics of Hugh Everett's many worlds model or theory interpretation. The parallel universes are all at right angles to each other. In this theory, this is because the electric and magnetic fields are always at right angles to each other, forming part of a process of continuous change that we see and feel as the continuum of time itself. And the mathematics of this theory is relatively easy to follow because it represents the geometry and the ratios of a dynamic process in three-dimensional space. So, from my perspective, the Earth isn't flat, but the universe is.
All right. Well, let me ask you this though, real quick. Like, what does it mean to you when you say that parallel universes are at right angles to each other? What does that possibly mean?
Well, it's the.
How do you envision that?
Well, I look at it as like the laws of motion and velocity, like the colliding of electrons and protons and neutrons. That, well,
I mean, if you were to experience one dimension and then experience an alternate dimension, it being perpendicular, would that have any perceptible or visible expression? I'm just curious.
Yeah, because the mass of something made of smaller parts is not just the mass of the sum of those parts. The total mass of the composite objects depends on A, how those particles are arranged and how those parts move within the bigger objects. And technically, Mass actually is an emergent property of energy, and it comes from quark potential energy, and it's bound basically by the Higgs boson, because if we didn't have these laws in place, um, we wouldn't even have a universe, because all particles would travel at the speed of light. So everything is very, in my opinion, fine-tuned. I mean, a lot of people don't
Well,
look at it that way.
just experientially, how do you imagine an alternative universe being perpendicular to your initial universe?
Well, if you look at
At right
like,
angles, whatever.
yeah, if you look at laws of acceleration and motion and velocity, and the way that particles interact with each other, then you know that's probably just the model of how the atoms and
Well, just from
their individual parts are interacting.
my humble opinion,
Well,
what I think of is that
okay,
that takes a lot. That takes a lot of work to. I mean, obviously, it takes a lot of work to actually answer that question or whatever.
Let's think about it this way.
But just let me contrast real quick. Is that is it so much harder to think of physics and think of the world in a flat plane, rather than a sphere? I mean, it seems like it's such a hard stretch for everybody to imagine that, but this is a pretty hard stretch too, to imagine alternate realities being at right angles to one another. I mean, anyway, I'm just pointing that out there. But,
okay,
so go on. I'm sorry.
For example, the way that the planets rotate around the sun, but they revolve as well. And in my notes here it says, why does the Earth travel in an elliptical orbit around the sun rather than just getting pulled in all the way? And this happens because the Earth has a velocity in the direction perpendicular, so a
centrifugal
90-degree
force
angle to the force of the sun's pull. So if you look at reasons why, it's because of laws of momentum and angular velocity, which I have in my notes here, but I'm sure somebody doesn't want me to start reading those right off.
Like centrifugal force would be angular velocity, yes.
But I wanted to ask you about your idea that it's electromagnetics that kind of runs your flat Earth model, but you don't believe in gravity.
Well, what does an inverse sphere mean? How do you visualize
like a concave disc.
How do you translate that, like in your head visually? How do you imagine an inverse sphere?
Well, because space-time is a fabric that's stretched out.
Okay, well, yeah, I don't know. I mean, I can't. I'm having a hard time, and it might be my simpleton nature of imagining an inverse sphere as well. But as far as electromagnet or gravity goes and tides, is that what you asked me about tides?
Oh.
What did you just ask me? I'm sorry.
Well,
I'm sorry.
yeah, that your model runs on electromagnetics. So yes, how do you account for the tides of the ocean?
Well, apparently there's some sort of slow undulation emanating from the North Pole, which draws the sun in its rotation, around it and the moon, and then there's a relaxing of it, which allows the path to expand. So I don't know, but maybe it's that same undulation in the sun and the moon. Maybe it's that same undulating intensity of the magnetic pole or the electromagnetic pole. Yeah, maybe that has kind of a maybe in subtler ways. I don't know. I'm just totally guessing. So so maybe that also affects the tides as well.
So on your flat Earth model, though, you got rid of the South Pole, but in electromagnetics, there's no such thing as a monopole. At least it's not impossible, but we've never found one naturally, and they're always dipolar, meaning you do need a south pole in your flat Earth model.
Okay, well, geographically, on a flat Earth, you don't need a south pole, even though you have the North Pole. But if you really consider what a flat Earth might look like, I mean, it has a top, and therefore I assume it has a bottom. And so if you remember the torus field around around the globe planet that we've seen, which gives shape to apples and fruit, and the reason they grow that way is because of that electromagnetic motion,
the Fibonacci sequence,
which also translates yes for conchs and things like that. Well, actually for everything, but if you have the flat Earth and you have the North Pole, perhaps that electromagnetic flow is going up and down just like it would on the globe, and it's coming out. And if we could see the bottom, I mean, if we have a top, there must be a bottom of this flat Earth, and so who knows what that's like. But perhaps if we could go there, we would be surprised to find that the electromagnetic field is actually spherical around the flat Earth.
Earth is a
so you
sphere,
could have
you have the firmament,
the land,
and you have the sphere underneath.
Well,
it is a sphere.
Well, the whole thing is
sphere, though.
The whole thing is, but not in the way that you and I think of it.
That's funny.
Topographically, it's flat. But when you consider the atmosphere, you consider whatever's below, and you consider the energy fields around it, perhaps it might turn out. Maybe there's a subfirmament as well, just caused because of the toral pattern of the electromagnetic flow on the planet. I don't know. What do I know? I'm a waiter. So, all right, your turn.
Okay, so let's talk about the Coriolis effect. Don't you want to?
Oh, of course I do. It's like you're reading my mind.
Well,
that's where you shoot, and a sniper has to adjust.
Artillery corrections.
Yeah.
Right, I have something about that, but let's just talk about the Coriolis effect first off. And the Earth rotates faster at the equator than it does at the poles. This is because the Earth is wider at the equator, so a point on the equator has to travel farther in a given period of time compared to a point spinning at the pole. The wind appears to bend to the right in the northern hemisphere and to the left in the southern hemisphere. Therefore, in the northern hemisphere, hurricanes and other storms swirl counterclockwise, while they swirl clockwise in the southern hemisphere. And pilots are aware of the Coriolis effect and take it into account when charting long-distance flights. This means that most planes are not flown in straight lines from origin to destination. So you might see a plane because they don't fly into the effect, they fly parallel to it. So you might see planes taking routes that flat earthers claim to be subject to scrutiny, because that's not the shortest point distance between 2 points. Is supposed to be a straight line, but that's not. Well, it's because they're taking into account the Coriolis effect. The Coriolis effect plays a role in the existence of the Earth's magnetic field. Magnetic fields produced due to flow of liquid iron in the Earth's core are roughly aligned in the same direction due to the Coriolis effect, which leads to the production of one vast magnetic field permeating the Earth. So that's it. I just wanted to introduce the Coriolis effect, and yes, they do use that effect in artillery correction. But what did you have a way that you account for that with just a North Pole and maybe a South one? Because now you might have a globe going on.
Well, somebody said
you might have a globe.
Somebody said, answering a question with a question is BS.
Yeah.
But that's the Socratic method. So I'm going to apply the Socratic method and say, well, people laugh at people that say, well, I'm going to go up in a hot air balloon and I'm just going to stay stationary, and I'm going to do this in England, and in about 8 to 12 hours, North America is going to roll up underneath me, right? Mm-hmm. And of course, that doesn't work. And the reason that it doesn't work is because, like, if you're on a bus and you have a ball and the bus is going at 80 miles an hour and you're just sitting there in your seat with the ball, if you throw the ball up, it'll still fall down because it's within an enclosed atmosphere, and the entire atmosphere is moving at a particular velocity.
Inertial frame of reference.
That is correct. That's correct. So how is it that if I'm going to shoot a gun and the bullet is going to get to its destination almost instantaneously, that you have to be careful to account for the Coriolis effect, Yet, if you're slowly just sitting in a balloon gently, and you can take hours, the Earth never rolls up
Okay, and I'm going to tell you why.
underneath.
Because during its flight, the projectile moves in a straight line, not counting gravitation and air resistance for now. Since the target is co-rotating with the Earth, it is in fact a moving target relative to the projectile. So in order to hit it, the gun must be aimed to the point where the projectile and the target will arrive simultaneously. And when the straight path of the projectiles is plotted in the rotating coordinate system that is used, then this path appears curvilinear. The fact that the coordinate system is rotating must be taken into account, and this is achieved by adding terms for a centrifugal force and a Coriolis effect to the equations of motion. When the appropriate Coriolis term is added to the equation of motion, the predicted path with respect to the rotating coordinate system is curvilinear, corresponding to the actual straight line motion of the projectile. For an observer with his frame of reference in the northern hemisphere, Coriolis makes the projectile appear to curve over to the right. Actually, it is not the projectile swinging to the right, but the Earth's frame of reference rotating to the left, which produces this result. The opposite will seem to happen in the southern hemisphere. And a soldier that I looked up mentioned that high angle missions, projectiles could be in the air 2 minutes, and not correcting it can cause the projectile to be off several meters. The Coriolis effect is at its maximum at the poles and negligible at the equator of the Earth. The reason for this is that the Coriolis effect depends on the vector of the angular velocity of the Earth's rotation. Just like what we're talking about 90-degree angles and other angles, and that affecting the reason that we think that the Earth is a globe.
So, all right, well, hey, you might be right, but so the Earth is moving so fast that when you shoot a projectile from a gun, that you have to calculate how quickly the Earth has moved from the time that the bullet is discharged before
it's actually
so it's moving that fast.
It's actually very minute. But if it's in a 2-minute trajectory range, that can make a big difference.
So let's say we shot a super slow bullet. I mean, would the Earth move so much that would really make it askew? Like it would move out from underneath it and change the angle that severely? Like what? What are you going to ask me?
Well, if you shoot a bullet in water, it's not likely to hit the target.
Well, I don't know. Something to think about. Interesting.
So I don't know. I'm not sure.
I don't either.
All right. So, and then another, because you asked me to do 10 proofs of why I think the Earth is round, and I think I've actually done like maybe 7.
Well, as a starting point, not as the defining structure of this conversation.
Well, I have talked a lot. I did a lot of reading,
it's good.
which is annoying to people.
No, it's good. People should hear that.
Nobody wants to hear someone just get on here and read. So, well, did you have anything to say about the Coriolis effect, or
not other than
you just don't believe in it?
Well, I don't know.
Pilots do say that they have to use that. They actually have a little box that calculates the effect for them. Which makes flying a lot more accurate.
I've heard testimonies from pilots and engineers saying that they don't account for that at all.
They don't, because they have a nice little box that does it. Because these are very complex mathematic functions of sine or whatever,
You mean that Y-shaped thing you were talking about?
No, I was going to look that up today, but I got sidetracked. But no, they're just functions of sine. So it's trigonometry.
Okay, well, what else you got?
Well, another thing I have is the Eötvös effect, which shows that not only is the Earth rotating, but that it's rotating about a central point that is underneath the ground, not somewhere on the surface. If you stand on the equator and face east, the surface of the earth is rotating in the direction you are facing and downwards, not left to right. So that kind of explains why the water doesn't just spray off the planet, because we're a globe rotating and revolving. This is actually just a measure of gravity, but it also kind of explains that, because if you stand on the equator and face east, the surface of the earth is rotating in the direction. Oh, I already said that. And furthermore, the cosine term shows that at equal latitudes, both north and south, the rotation is at the same angle relative to the surface, which can only be the case if the earth is symmetrical about the equator, i.e. spherical. Gravity measurements taken while the ship was moving eastward were lower than readings taken while the ships were moving westward. Etvo realized that this effect was being caused by the rotation of the Earth. The Earth's equatorial circumference is 40,075 kilograms, and it rotates eastward once every sidereal day, which is 23 hours and 56 minutes. So the ground at the equator is rotating at a linear speed of 465 meters per second. To move in a circular path rather than a straight line, as indicated by Newton's first law of motion, gravity supplies a centripetal force to any object on the Earth's surface. The necessary force is equal to the object's mass times the velocity squared divided by the radius of the circular path, so 6,378 kilometers, and that comes to 0.0339 meters. So per kilogram of mass, a force of 0.0339 newtons is needed to enforce the circular path, an amount easily supplied by Earth's gravity. And this, like I said, is why objects don't get flung off the Earth by its rotation. What this all means is that the effective acceleration due to gravity measured for an object sitting on the equator is reduced by 0.0339 meters per second squared, in the same unit as the 0.339 newtons per kilogram, compared to if the Earth were not rotating. But if you're on a ship traveling east at, say, 10 meters per second, the centripetal force required to keep you on Earth's surface is greater, equal to, it's a big number, but 0.0354 newtons per kilogram, because it also has the mass. Or, I mean, the, shoot, now I'm getting confused myself. But it also has the, whatever. Anyways,
okay.
this reduces the apparent measured gravity by larger amount, making the measured value of the gravity smaller. And if you're in a ship traveling west with the same coordinates, reducing apparent gravity by a smaller amount and making the measured value of gravity greater. So basically, he set his ships traveling north, south, east, and west. He predicted that the gravitational pull would be such and such, and then he measured it and he proved out his predictions, which indicate gravity of that specific measurement.
Or possibly electromagnetic force behaving in the same way. But of course, again, if it's on a circular globe, what can I argue against that? So, this no longer has the bar feel, but I mean, that's something that has to be considered.
But if there was a flat Earth, there would be no Eötvös effect at all, because there would be no centripetal acceleration. And even if the flat Earth did rotate around a pole, the centripetal acceleration at every point on the surface would be parallel to the surface towards the pole rather than below. But the force being below is what causes the water to stay. If it was parallel, sure, it would just like fan out.
So that would explain why rocks, huge giant rocks, don't attract suddenly the smallest little drip of water and hold it to it, because it's not, the rock itself isn't
Well, it doesn't
moving
have very
around.
much mass, does it? So it's not going to have a very big
Well, I'm talking like
Newtonian gravity
let's say
pull or whatever.
Gibraltar, right?
Yeah.
And then one drop of water.
Yeah.
I mean, I don't think anyone has ever seen a drop of water get pulled to it and stick to it permanently.
Right,
because
it's
of
a
the
bigger system. It's not.
Well, anyway, all right.
Okay, because first of all, with the electromagnetics, the wave functions have to find a place to meet. I mean, uh, oh, but you're talking about gravity, right?
Yeah. Well, yeah, but whatever.
But
Anyways,
it's so minute.
okay, all right, whatever. Either way, this inspires me to, or has inspired me to think about other things. But we've already gone on longer than we usually do, so we're gonna end it now. But we're gonna come back. This has only begun.
That's
And thank you
threat,
for watching.
I promise.
If you've actually watched.